Ladies and gentlemen, here is our next speaker, Dr. Domenico Balsamo. Dr. Domenico is from Newcastle University, Northeast England, United Kingdom. He is here with us to share about energy-driven computing for IoT. A warm welcome, Dr. Domenico. It's a delight to have you here, and I'm excited to hear from you. Next 25 minutes is yours, and please take over the period.
Thank you very much. I will share my screen if that's fine.
Yes.
Okay, brilliant. Screen. Just can you confirm you can see my screen with the slides?
Yes, Dr. Domenico, we can see.
So I will just put the slides larger. Can you see the full screen with the slides?
Yes, yes.
Okay, great. Okay, well, thank you very much for inviting me, and I'm very happy to be here. Good morning or good lunchtime to everyone. As already being introduced, today I'm not really going to talk about, or at least directly about AI, but I will be mostly talking about IoT systems, or more specifically about energy-driven computing for IoT systems. And I'll give you more details during the presentation of what do I mean for energy-driven computing. Just let me know if there is any technical problem or issue in terms of slides or what. I think you can probably, I'm not sure I'm sharing the right screen, so just bear with me 1 second. Yeah, I think this is the right one. So you should be able to see the whole screen with the slides. Is that correct?
Yes, yes.
Yeah, brilliant. Okay, so just let me give you a bit of background. So I'm currently in Newcastle as a lecturer on the microsystems, hardware and software design for microsystems and IoT systems. But before moving to Newcastle, I was working in Southampton, so University of Southampton, and in there I was working on this Prime project. This was an EPRSRC founded research program which brought together different expertise in terms of parallel embedded computing. And the overall aim of this project was really working on multi-core embedded systems and making them more reliable and increasing the energy efficiency of this multi-core embedded system. And in some terms, we during this big grant we touched some of the aspects related to machine learning applied to runtime management. Okay. So in parallel to that, I was also researching various aspects, including hardware design, power management, mostly on the wireless sensor network and body area network side. Okay. Is everything fine with the screen? I guess so. Okay, so today I'm going mostly to talk about IoT nightmare. So the previous speaker has been introducing the IoT topic, and I would like to go a little bit more farther on this topic. And one of the problems with IoT systems is emerging as a primary challenge is how do we power devices within the Internet of Things? And the overall idea is that we shouldn't intervene to replace batteries, change batteries when these batteries are currently depleted. So one possibility is considering some form of energy harvesting sources. So the way of you can actually harness energy from the environment or from the human activities, from the human body, for example. And can energy harvesting systems be used to replace battery systems? So this is a field of research that has been going for a bit of time, but there are still some fundamental issues that I would like to highlight. So in here you can see different technologies that so far have been used with different types of transducers that you can use to convert different forms of energy into electricity. And so you can see heat in here, motion and vibration, light, RFID signals, so EM energy, thermal generator, thermoelectric generator, airflow, so you can use wind turbine, the sun, so the light using PV cells, photovoltaic cells, electromagnetic field, and etc. But there is one fundamental problem with energy harvesting systems. So ideally the power, the instantaneous power, can be considered infinite. But in practice, the power is most likely unpredictable or uncontrollable or scarce. And this really depends on the source characteristics. So it depends on the type of transducers, it depends on the type of environment, and etc. So the challenge is ideally we have infinite power. In practice, we need to be able to manage this power, and definitely differently from what we have been doing with battery powered systems, with their battery powered counterparts. And in this sense, I would like to highlight a little bit more this aspect. So in here, you can see how dynamic and uncontrollable the power generation can be from an energy harvesting system. So I just collected some data from a PV cell over time and from a micro wind turbine. Now in here, you can see that the type of signals, the type of power or voltage, they are really, really different. Therefore, systems need to adjust to different types of sources. Now, a paradigm that has been introduced is the energy neutral operation, in which what you can currently do, you add a storage, and most likely a big storage super cap of rechargeable batteries. And what you try to do is honestly try to moderate, accommodate the energy that has been harvested versus the energy that has been consumed over time. And this type of circuit, they usually include also some form of maximum power point tracking circuiting. I'll invite you all to interrupt me if you have any question over the presentation. So ideally what you can have is a big storage, you store the energy, and then when you have enough energy to do something useful computationally, you actually do that. But I see some limits in this approach. So in the first place, there is an increased volume, weight, and cost in terms of the overall device. But also you need to wait time, and this time can be quite unpredictable while you are waiting for the storage to be charged. And usually this kind of mechanism, this kind of process deteriorates over time in terms of performance. So, well, I just moved with my research in a slightly different direction. And I said, well, let's think what is the fundamental problem. The fundamental problem is the mismatch between the power harvested, the power availability, and the consumption of the power. So I thought maybe we should just design systems with this potential mismatch in mind, in which the current operation, the current execution is kind of interlinked with the power or energy availability. And therefore, can we design systems to have storage that is relatively small, so not necessarily big energy storage when compared to the average power consumption. And I kind of defined the concept of energy-driven systems, in which the energy source and its availability is one of the key points, the key consideration in the system design. Now, probably this doesn't really say much of what I mean for energy-driven system. Therefore, I've been defining some points around these concepts, kind of 4 pillars. The first one is transient computing. So when we work with energy harvesting, what we are expecting is to have this unpredictable and uncontrollable power supply. Let me know if there is any problem in the presentation, okay? So power supply, and ideally what you would like to do is to survive to power outages. This might happen when you profile energy harvesting systems. Okay, so the first aspect is how can we make system resilient to power outages? Because this most likely is going to happen when you use unreliable or uncontrollable power source. So in this sense, what I conceptualized is this transient computing approach, in which we can enable computation to be sustained despite power outages. And now this is happening. So I worked a bit on this topic, and I wrote a few papers on this topic. I'm happy to cite some of them in here. And the overall idea is, how can we save the system state as fast as we can? And then when we have again energy available, we can currently restart from where we left off. Okay, so the overall idea of Hibernus is quite simple but effective. So what we really do is, by controlling the power source, the voltage supply, we can hibernate the system state using, for example, a fast non-volatile memory, such as an FRAM or an MRAM. And actually, you can restore the system state quite quickly and continue from where you left off. And I implemented this kind of approach, in which you can see in here that it's a flow chart and a library as a library. So you can just include a header file and make your system non-transient. So your processor, basically a non-volatile processor. So I prepared a video. Can you see the video in here? Okay, I'll just run this video. I hope it will run. Okay. Okay, you should be able to see this video. So in here you can see a wind turbine, and what is happening is that while we are blowing is continuing, is a binary counter. And in here, every time we don't start from scratch, we start from where we left off. And ideally what we are doing, I'm showing here the wind supply, so this directly applied to the system. And you can see in there that you can actually save the state, restore the system state, and you don't have to start from scratch every time. And this is happening just by including actually a library in your code and just adding the function Hibernus within your code. So this is the overall idea. Then I moved a little bit farther and I said, well, I don't really want to have static thresholds for saving the system state, but I want to adjust these to the type of source. So I want to learn from the source, and I want to make this saving and restoring process as efficient as possible. Therefore, I then designed Hibernus ++, that is really an updated version, an upgraded version of what I was showing before, which takes also into account very tiny, very small energy bursts of energy. So I asked myself, is this enough? Is this enough? And I thought, well, it's enough when we are dying, when our system is dying, but it's definitely not enough when we want to use effectively our power or energy while we are doing something useful. So I moved from energy neutral systems to power neutral systems, in which what you actually do, you try to match the power availability with the power consumption in a kind of proportional way. And what you really do is adjusting the system's performance really to the operating point of your system dynamically. So by changing the operating point, you can also change the power consumption of your computational unit. And you can match these two things, or try at least to match these two things. So ideally, I just try to summarize this, the major point. So what I was looking for is power neutral operation where the system performance is actually adjusted at runtime to match the instantaneous energy harvesting supply. And additionally to this, I also been consider automatically the maximum power point tracking of the source. And in this way, ideally, you can make forward process and therefore also higher throughput on your computational part. So I then defined momentum, that is really mostly a software-based approach that is conceptualized for power neutral systems. And this also includes what I was presenting before in terms of hibernation. And the overall idea, as I said, is to try to estimate or measure the power consumption and kind of confine the operating point of your system within a defined behavior depending on the power consumption. So just for matter of time, I will show you overall picture of what I've been doing on this control system. But I believe if you have any question later, or you have more, you want to have a little bit more insight about this topic, I'll suggest you to have a look to this paper that is from 2019 on power neutral approaches. Great. So is that enough? So on the other side, what I've been thinking, that one thing that is currently missing in here is the application side. So in terms of application, most likely the applications will work in a kind of task-based approach. And when you move towards multi-core systems, you might have like multiple tasks happening concurrently, for example. And in this sense, one of the questions that I've been wondering is, I forgot something, is the application. So the important bit is the IoT application. And in here, what you need to consider is the energy burst scaling depending on the task that you want to execute. And additional to this, I also thought about having some kind of opportunistic triggering for the application. For example, if an event is happening, or can we do something, or can we adjust our operational mode depending on the state of the system? So to give you a little bit more insight about this, what I meant in this sense is, okay, usually what you have, you put your system in idle, so what is happening traditionally, then you do some form of sensing, you do some form of processing, and eventually we are considering an IoT system, you will send the data over. And in this sense, you have always on system with low constant power in idle on sleep mode. When you move to a more task-based control system in which you can exploit somehow the transient computing ability, what you are currently doing is introducing the zero power mode. So you do maybe some sensing, and then you can currently, your system can just shut off, die, and then you do the processing bit. And then you, again, you can kind of rely on the fact that you can save the system state. And then you do the transmission. So therefore you can reduce the energy storage, because the maximum energy storage you need is just for the biggest task, that in this case is usually the processing, especially if on the top of this board you are using some form of machine learning approach. And in this sense, what I'm moving forward is, okay, can we split this computational task, that is the processing task, that is the most computational intensive one, is small pieces, as this is not really affected by the need of being completed within one burst. But there are some issues. And these are the issues that I'm currently, in my research within my group in Newcastle, trying to solve. So the first point is, okay, if I'm breaking my system down, I will struggle to have track of time, what is happening in there. And we know that in IoT system, when you are sending data over, it's very important to have an idea of the time when things are happening. On the other sense, can we adjust the quality of service? So for example, when you work with convolutional neural network, general neural network in general for the processing part, can we adjust the, for example, the number of layers depending? So can we have some form of levers in which we can currently adjust the computation to the energy availability? As I said, this is still questions that I'm trying to face in this sense. But the overall idea is, by using approaches that are mixed between task-based and reactive as Hibernus, what you can currently do is bringing the energy storage to the lowest point, and at the same time face some kind of interesting research challenge that I'm currently addressing. There is one more point that is, I will leave you with these open questions actually. And then maybe if you want some of the answers for these open questions, you can ask me questions later on. So there is another aspect when you work with transient computing systems. So you might solve the problems at the CPU side or at the processor level, but then the system is, the device is not standalone. It interfaces with other people, with other nodes within the network. So there is a fundamental research problem that is stopping the transient computing to go with the IoT systems or to be fully implemented within IoT systems. That is, okay, let's assume I have this node that is ready to transmit, no? So what is happening if the other node is not on because it doesn't have any energy? So it becomes a protocols in IoT system, they are mostly based on synchronous. So they are synchronous protocols. So they rely on the fact that you will have your time slot for transmitting data. And this is assigned when you do the joining of the network. And this can be changed dynamically, but in any case, you rely on the fact that you can have a time that is kind of common for all the nodes within the network. This is a problem when you move towards this kind of systems. So in here, I think as a possibility is that, okay, the harvesting process must be incorporated, not just for sensing, but must be incorporated in the network model in the first place to be effectively utilize the harvested energy also for guaranteeing some form of reliable communication with intermittent nodes. Probably this doesn't say much, but I can give you a little bit more insights about this if you're interested. So some techniques that they are currently in development are like simultaneous wireless power and information transfer. So concurrently, you can transfer information to the neighbors and power at the same time. So this is the direction I'm thinking for the future of this system. But so being conscious about the time, I can see in here is already 24 minutes, my presentation. So I was supposed to talk for 25 minutes, so I will probably stop here. And if you have any other question for later, I'm from Newcastle. My colleague tomorrow, Richard Safek, will give you more insights about the work that we are doing within the group, more on the AI side. I just focused on like problems that we are facing empowering the Internet of Things. Okay, thank you very much.
Thank you, Dr. Domenico. Energy harvesting sounds wow. Different technologies of energy harvesting, it's great. Every national citizen should understand what you have projected, Dr. Domenico. It was incredible. And thank you for joining, devoting your precious time and knowledge with us. And of course, you placed a challenge in front of us in terms of energy.
Visit our website, citeracademy.no, for more information about our training programs, boot camps, courses, conferences, research publications, Microsoft and Cisco certifications.